Hello all and welcome back to physics. Today we are actually going to start physics. Woohoo! I know I'm excited. You guys probably aren't as excited as I am, but it's fair. We are going to do some vocabulary today. Our first three words are on my screen here: position, displacement, and distance. These three words have to do with your place in the world. Where am I? That is the question that these questions can answer. Position tells you where something is. If I say Corey is over there, well, that's all well and good, but where is over there? Is it above me? Is it below me? Is it to the left, to the right? There's no way to know. If I say Corey is 10 feet from your door, well, that's at least a little bit clear where Corey is standing. Maybe they're 10 feet in front of the door, maybe they're 10 feet behind the door, maybe they're 10 feet below the door. We still aren't quite sure yet. So, position is the location of an object of interest in space relative to a fixed point. So, in that example, Corey is 10 feet from the door. The fixed point is the door. It's something in your field of view that you know exactly where it is. It is your point of reference. That is your 0 point. Okay? The location of Corey, or Corey's position, is 10 feet from it. It could, let's say he's 10 feet to the left of the door. That would mean that he's standing 10 feet from that fixed point, in fact, to the left of it from your point of view. So with position, we're just being very, very specific about where something is located. Displacement, it says, is the overall change in position, or the as the crow flies motion, if you've ever heard that expression before. Distance is the sum total of movement regardless of direction. So let's take a look at an example of this, because this can be a little confusing when you're first starting out. If we look at this example here, it says Ruby drives to the grocery store from her house along the route shown below. What is her displacement from the house, and what distance did Ruby travel, or how far did she end up going? So this is saying that she's just going to the store. It's not a round trip. Okay? So total, we could see she went 14 meters to the right from her house, and then 20 meters down from her house, 47 meters more to the right, and then 6 meters north. To get her total distance, the sum total of the movement, no matter what direction, we can just add these arrows together. 14 plus 20 plus 47 plus 6. And that'll give us 87 meters. However, her displacement is a bit trickier to get, because it's this as the crow flies motion, which means it's this motion as if she went straight to the box store, as if there was nothing in her way. Now, if you're ever walking to, say, like a friend's house or something, you know there's other houses in the way, there's different street corners, maybe you gotta cross railroad tracks. There's things that get in your way, and that straight line path, it's not always possible. But if you were a bird, birds can just go over all those obstacles, and they just don't care. That's what that as the crow flies motion means. It means regardless of anything that could be in their way, they can just go straight there. Nothing matters besides that. So we're going to need to do some fancy calculations to solve for that. Now this example is a little more complex, and I did do out all the math here on your notes page. However, I'm going to do a slightly simpler example with you to look at this. Let's say that this is the route that Ruby took to get to the grocery store instead. Our distance here would just be the total sum of these three arrows. So we would add 5 plus 3 plus 1.2, because again, the distance does not care about the direction. So distance equals 5 plus 3 plus 1.2, and gives us a total of 9.2 meters. Now, if you don't know what a meter is, this is actually an absurdly small amount of distance. This basically means that Ruby had to walk down her front steps and then around a fence to get to the giant eagle. But it's just an example. Now, for her displacement, this cares about direction. This again is that as the crow flies motion. So that's as if we went straight from the house to the grocery store along an arrow like this. So you might be looking at this and like, I don't want to deal with two different triangles. Come on, that's just way too much work. The nice thing is we can just add these things together. I'm going to turn this into just one big triangle. So the red is the new triangle that we're going to deal with. This side, we'll call it X, is the total of all of the movement in the rightmost direction, or in the X direction. So X would be 6.2 meters. So that side of the triangle now is 6.2 meters long. And the total that she traveled south is still 3 meters. So now we have a new triangle to deal with, which I'm going to redraw down here. Now, to figure out Ruby's displacement, we're going to use our Pythagorean theorem. This is part of the reason that we started with our math review. So to find Ruby's displacement, we're going to need to use a squared plus b squared equals c squared. Now, c is always going to be that longest side, which in this case would be the displacement. So it does not matter which side we let a and b be. So I'm going to make the 6.2b and the 3a, just because. Plug these in. 3 squared plus 6.2 squared is equal to c squared. That means c is equal to the square root of 3 squared plus 6.2 squared. C then is equal to the square root of 9 plus 38.44, which I just put into my calculator. I do not know that off the top of my head. C then is equal to 47.44, square root of 47.44, which is 6.89. Now, before, we weren't dealing with real-world examples, and so with it being pure math, there were no units. However, now we are talking about the real world. There's real distances involved, and so we need to put those units. In this case, it would be meters. So her total distance was 9.2 meters, and her total displacement is 6.89 meters. One thing that you should notice with these problems is that the displacement is always going to be less than the distance. And that is because, if we look at this picture again, that as the crow flies motion, it ignores everything else. So of course that route should always be shorter than when you have to go around all of the buildings. Okay? Now our next definition is speed. Now, all of you, I'm sure, know what speed is. It's just how fast an object is moving. What people always get confused by is the difference between speed and velocity. All velocity is speed, but with a direction. So instead of saying the car is going 60 miles per hour, you would say the car is going 60 miles per hour east, or 60 miles per hour north, or 60 miles per hour south, and so on. The big difference is just the direction. We want to know how fast it's moving and in what direction it's moving. If we just have how fast, that's a speed. If we have how fast and the direction, that's the velocity. And in physics, we really don't care much about just the speed. we really need the velocity, because it's going to make a much bigger difference as we start talking about how things are moving in the real world. If I tell you that something is moving south, or maybe instead we're talking about a skydiver. If a skydiver is falling at a rate of 30 meters per second, we can pretty much assume he's going to be falling down towards the earth and not, 30 meters per second straight off into space. That wouldn't make any sense because of gravity. We're going to really be paying attention closely to these directions, especially as we get more and more advanced with our topics. And our last main definition is acceleration. Acceleration is a change in the velocity, or a change in how fast something is going in a certain direction. So it's the biggest difference between real life and cartoons. At first, we're going to be looking at situations like in cartoons, where as soon as something decides to start running, it's immediately running at full speed. It doesn't have to work up to a certain speed. But as all of you know from gym class, if you want to run a really good mile, you're going to have to first build up your speed. Or if you're doing a 50-yard dash, for example, you're not immediately going to be running at full speed. And if you have a wall at the end of your route there, you're not going to want to be going full speed at the end either. So acceleration is just how much are you speeding up or slowing down. It's what happens when you step on the brake in a car, or if you step on the gas. If you step on the gas in your car, you are accelerating. You are increasing your velocity. If you step on the brake, you are decelerating, or decreasing how much velocity you have. Now, I have a silly example for you all. We're going to look at how this looks like in real life. And, it just didn't seem as interesting to look at a typical car race, or just watching a car drive down the street and then have to stop at a red light. We could do that, sure. But personally, I thought this would be a little bit more fun. So far, we've already seen a change in position as the car moved down the hill, and we saw it decelerate as it came to a stop.
Man, the roads around here are in terrible shape. It wrecks your car and it limits your speed. It's almost enough to make you pay your taxes. But rather than do something I know I'll regret later, I've been trying to find a way to smooth out the ride. Now, this one worked great the odd time the helmet actually lined up with the pothole. Other than that, it felt like you were walking with one high-heeled shoe on.
Now, if you've ever been driving and hit a pothole, you know how jarring it can be. Mr. Red Green here is just trying to figure out, well, how can I make it so when I hit a pothole, it doesn't make me decelerate, it doesn't make me slow down, and it doesn't disrupt my driving? And, well, his first invention wasn't quite the best.
Not that I've done that. Now, this one wasn't totally successful because I forgot that Bernice is allergic to feathers. I even tried filling up the potholes. Everybody at Bernice's work gets one of these totally uneatable Christmas cakes every year for the last 35 years, so we got a fair whack of them. And if you flip them over, they're the same size and shape as a pothole. The trouble is, after 35 years, the Christmas cakes are in about the same condition as the road.
They have another issue too. If you hit anything in the road, it's going to make you decelerate or slow down. So it's still going to disrupt your velocity.
But then in today's paper, something caught my eye. Right about there. No. I was looking through the personals to see if any of my old girlfriends would come to their senses, when I saw some guys trying to unload an above-ground pool. And I'm thinking, hey, that could be just the ticket. Now, I don't have any money to give them, but maybe we can work out a trade of some kind. We'll see.
One thing you have to know about Red Green, he is very poor and very, let's call him inventive. not always super smart.
Okay, that was a mistake. I should have emptied it first.
One thing you might have noticed as that car decelerated and came to a stop is that the water on top of the car didn't stop with the car. It continued to go forward. That is because the water on top actually has a separate velocity because its position is different. So the way that it decelerated was also separate.
The only thing I need from the pool is the side. I'm cutting it in half so I get 2 wide rings of sheet metal. It's light, it's durable, and it's smooth, a lot smoother than the roads around here. But I'm not going to be driving on the roads anymore. I'm going to be driving on these babies. Maybe I'm getting a little ahead of myself, but I'm just trying to keep up with you guys. I'm using these lawnmower handles as guides for my pool sides. Of course, taking the handles off the lawnmowers means I can't cut the grass, so it's a win-win. The idea here is to put something between your tires and the road. Something that'll smooth out the bumps. Kind of like what your wife does between you and the neighbors. Funny how slipping a ring on can change your life forever. Now I'll just glide over the potholes. And here's another bonus. Real easy to find this car in the parking lot. So remember, if the women don't find you handsome, they should at least find you handy.
Now, Brett is going to actually drive this car, as amazing as it sounds. And as he starts to drive, I want you to pay attention to what the wheels are doing.
And if the cops pull you over and ask you what the heck it is, tell them it's a carpool.
Notice that the wheels are actually sliding the pool tarp, I suppose, along the ridges. So even though the pool tarp is staying in position with the car, it's pushing it, so it's actually creating a different displacement for the car itself. Now, one thing that Red probably didn't account on, and why this video doesn't go on for very long, is that stopping this car is going to be quite the ordeal. You see, the way your brakes work is that they create friction between you and the ground. And without being able to create friction between you and the ground, and only friction between you and the pool, well, you're going to have a much harder time decelerating or bringing your velocity to a stop. I also don't recommend bringing this up to a very high velocity, a very high speed in any given direction, or trying to turn lanes, because if you turn your tires to the right, there's a good chance it's going to slide right off those pool tarps. Okay, so that was our brief, silly introduction to the vocabulary of motion. We will be using this vocabulary to do some different problems throughout next week. Your assignment for this week is simply to think about how these words are used in everyday life and how they apply to everyday situations. You see, in physics, we will be getting just a lot of word problems, and I want you to be able to recognize how these words are going to appear in different types of problems. So that is your focus for today. Other than that, enjoy your weekend, and again, office hours will be Thursday at 1 o'clock if you need help with anything else.